Good evening to everybody. It's really my pleasure to welcome Professor Piramanayagam. So everybody knows him as Prem, and he's going to talk on an exciting topic of neuromorphic computing. You may know him very well, but as a matter of formality, so I would like to introduce him. He has got his master's degree in physics from University of Kerala, Trivandrum, in India, and subsequently he moved to Indian Institute of Technology in Bombay for his PhD degree, and then he pursued some further research at Shinshu University in Japan from 1995 to 1999. After that, he was an adjunct associate professor in National University of Singapore between 2003 to 2010. And also between 1999 to 2015, he was mostly working at the Data Storage Institute in Singapore as a senior scientist. And since 2015, he has been full-time academician as an associate professor at NTU in Singapore, Nanyang Technological University. And as you may know, he is working really very hard on the topic of spintronics. Since last 30 years, he is in the topic of magnetism, starting from amorphous magnetic alloys for energy applications, permanent magnetic materials to thin films and nanostructures for recording and spintronics applications. Obviously, he's working on nanotechnology, spintronics, magnetic recording, and energy. And he has recently secured a multi-million-dollar grant for research on spin-based neuromorphic computing. He's a senior member of IEEE Society. He served as an editor of IEEE Transactional Magnetics, an editorial board member of Scientific Reports, Physical Status Solidity Rapid Research Letter. He has served as the chair of IEEE Magnetic Society. He has more than 175 publications in high-ranking journals, several patents. He has also edited a book titled Developments in Data Storage, Materials Perspective, and many PhD students, master students have graduated under his supervision. So with this, I really welcome Professor Piramanayagam for this webinar, and thank you all for joining. Unfortunately, I have a medical emergency in family, so I have to leave, but my colleague Dr. Brajbhushan Singh is here. He will coordinate the webinar. And if there are new participants, just a small request that we take the questions at the end, and feel free to write your questions in the chat window, and me or Braj will take the questions at the end, and we will try to address all those queries. So
thank you,
Subhankar. Prem, I request you to start your webinar. Thank you.
Yeah, thank you, Subhankar, and team at NICER. Good evening, everyone. It's my pleasure to give the talk on spintronics-based neuromorphic computing. So before I get into my talk, I'd like to thank my co-authors. Durgesh, Jampeng, they are my current PhD students. Tianli is my past PhD student. They did most of the work. Particularly, Durgesh has done a lot of work in this in today's talk. And I would like to thank my collaborators from IMRI, A-Star, Singapore, and also Professor Sbia from Sultan Qaboos University, Oman. And this project is funded by a major grant from NRF Singapore under the CRP program. Then we also have partial support from A-Star grant. So I would like to thank the funding agencies. And this is the team that we have assembled to work on the spin-based neuromorphic computing. So we have researchers from physics background, material science background, and electrical and computer science background. So together, we are going to solve many problems related to spin-based neuromorphic computing in the next 4 years. So the outline of my talk, firstly, I'll introduce the neuromorphic computing. Then I'll again spend some more time on introducing the spin-based neurons and the synapses. So about first half an hour will be basically tutorial type of talk where I'll be introducing the basic stuff. Then I'll move on to discuss the core work of our group. Firstly, I'll be talking about domain wall pinning, which is an important aspect of neuromorphic computing. Then next step, we'll talk about the recent developments in the energy reduction aspect for domain wall motion, because this is also crucial for spin-based neuromorphic computing. Then finally, I'll summarize my presentation. So if you look at the history of electronics, when I say then, I mean 30 years ago. At that time, we used to have like different devices for different purposes. So we used to carry a Walkman for listening to music. So if you want to record songs, then you should have another device. So we have a separate player for video, separate camera for video, separate camera for shooting still, and things like that. This was the situation 30 years ago. And many people may have access to only one or few devices, not all the devices. Whereas if you look at the situation now, you can do all these aspects in a single smartphone that you carry. So you can record songs, play songs, you can record video, shoot stills, and so on. So many things you can do in one smartphone. And this kind of growth is coming from the traditional scaling of semiconductor technologies. So when I say scaling, it's basically reducing the dimensions of transistors or increasing the physical parameters of certain parameters like dielectric constant and so on. So scaling is proportionately increasing or decreasing something to achieve your objective. So in the case of semiconductor scaling, we have moved from 3 micrometer process in 1978 to 14 nanometer process in 2018. So because of this kind of reduction in the pattern sizes and so on, we can pack more transistors. So in 1978, we could pack like 29,000 transistors in a processor, whereas the processors of this current decade are have billions of transistors. So this kind of traditional scaling has been happening for many years, but this cannot go on forever. So this is getting stagnated. As a result, people are looking at new architectures and new materials. So when we talk about the new materials, the semiconductor industry has already looked at the roadmap. They have been doing semiconductor materials. Then about a decade ago, they decided that we should also look at spin-based materials. So when they say spin-based materials, it's basically ferromagnetic material, spintronics materials, and they have took this objective and they have worked on magnetic random access memory for the past 1 decade. And because of that, now they are ready to ship the magnetic random access memory devices. So this is becoming commercial reality. So this is one thing that's happening in the semiconductor industry. Secondly, the artificial intelligence is now getting wide implementation. So if you look at major electronics players, like Apple has Siri, Google has a Google Assistant, Amazon has Alexa, and so on. So these devices are picking up and they are using artificial intelligence. But one of the major problems with the artificial intelligence is that the power consumption. So these devices consume significantly large power. So if you Google and search the iPhone battery and Siri, then you will have a lot of issues like this. So basically, artificial intelligence applications drain battery power. So this is a serious problem. But if we can somehow increase the power efficiency of the artificial intelligence applications, then we can prolong the duration of the use of the devices. For example, if you use Google Glass to, suppose Singapore Airlines decides to give a Google Glass to the flight attendants, so that they can recognize the passengers and serve them accordingly. This is possible with Google Glass, but the main problem is the battery will be drained in about 25 to 30 minutes. So that's a serious problem. Whereas if we can improve the energy efficiency of artificial intelligence applications, then we can have more practical applications of artificial intelligence. So that's where this talk is coming from. Don't worry about the language here. Basically, I want to say only 2 points from this picture. Firstly, artificial intelligence is very old, older than what you may think. It's actually older than internet. So that's number one that I want to show here. Secondly, the artificial intelligence has seen many ups and downs. So there were some peaks every 10 decades, every 2 decades or so. There has been peaks, but there is also declining interest and so on. But in the last 2 decades, there's a growth in the artificial intelligence technology. So this is something to note. And this interest mainly came after the major breakthrough in the artificial intelligence, when a computer beat a human. So in this case, Deep Blue is the computer built by IBM. So it's a supercomputer capable of imagining 200 millions of chess positions per second. So that kind of computation it can do. And with this kind of computation, for the first time ever, the computer beat the world chess champion in 1997. Okay, so this was a major breakthrough in artificial intelligence. But if you look at one aspect of this game, the supercomputer used megawatts of power to calculate its move, and the human uses only 20 watt. Okay, the brain of the human uses only 20 watt of power. Okay, so this shows the difference between the artificial intelligence and the natural intelligence. Okay, so the natural human intelligence works at very low energy. So it has very high energy efficiency, whereas the artificial intelligence applications have very low energy efficiency. So this is a problem that we need to tackle. And if we think about the origin of this kind of inefficiency, one main aspect is the architecture that we use. So if you look at the current computing architectures, we are using the von Neumann architecture. So in this case, this is like a 7 decades old architecture. In this case, we have a CPU. The CPU does the process and it fetches the data from memory. And when the computer does the calculation, the data flows between the memory to the CPU and back to the memory and so on. This kind of to and fro motion happens. And this is the architecture used by the artificial intelligence applications. Only the algorithms are new. Okay. So if you want to give some analogy, if you look at the computer, we have the CPU here, and the memory is somewhere here, around 4 centimeter away from the CPU. So if you assume that the transistor has a size of 40 nanometer, so compared to 40 nanometer, this 4 centimeter is equivalent to a human walking a distance of 1000 kilometer. Okay. So imagine going to a place 1000 kilometer to fetch some data. So this kind of fetching data back and forth between the CPU and the memory takes place in the computing architecture as of now. As a result, we have significant energy inefficiency. Whereas if you take the neuromorphic computing is taking inspiration from the brain. So we are going to mimic some aspects of brain and make the intelligent computing as a power efficient computing. So in this case, we have to develop new hardware, we have to develop new algorithms, and the new architecture, which includes these elements, will be called neuromorphic computing. So that's what we are trying to do with spintronics. And so when we want to understand neuromorphic computing, it's also good to know a bit of how the brain works. So don't worry about so many terms that you see here. Basically, people know certain aspects of brain, but they don't know everything about how the brain works. But they know that in brain there is something called a neuron, and neuron is like the processor of information in the brain. So they receive inputs from many other neurons, and when the input signals reach a critical potential, they will give a spike. So this spike will travel through the axon to the other neurons through something called synaptic terminals. So here what you see in this video is animation is the spike signal going from one neuron to the another neuron. And the neurons are connected to each other through something called synapses. And these synapses are the memory elements of the brain. So the information is stored in synapses. And these are the bridges between two neurons. Basically, their job is like the connection between two neurons through a synapse is big when the learning is not achieved. And the connection becomes stronger as the learning gets better and so on. So the weight which determines the learning keeps increasing as the learning happens. So that is the main aspect of synapse. So these two are the key elements of neuromorphic computing. And we are trying to build some of the elements like neurons and synapses in our project. So this is a brief introduction to spintronics. Many of the students already know that in spintronics we make use of charge as well as spin, whereas the conventional electronics we mainly make use of the charge. Okay, so that's enough for this slide. We move on to the next slide. The first major breakthrough for spintronics was the observation of giant magnetoresistance. So Professor Furt, who is shown in this picture, and Professor Grunberg, they discovered the giant magnetoresistance. So in this case, we have two or more magnetic films separated by another metallic non-magnetic film. So in this case, if the two layers have parallel magnetization, the resistance is low, and if the two layers have anti-parallel magnetization, the resistance will be high. So this is arising from spin-dependent scattering of electron, and this is one of the first useful invention. Useful means commercially applicable physical phenomena of spintronics. So this is the first case. So the second, GMR actually was very helpful in pushing the hard disk capacity. So from 1 bytes of data make more sensors. The second, so in comparison to the GMR, can you hear me?
Yeah, we can.
Yes. Yes, sir, we can hear you.
Yeah, please continue. We can hear you.
Okay, I think sometimes the internet is slow or something like that. My audio might have been lost.
Yeah, it was breaking, but now it is fine. Yeah. Oh, shit. Okay.
So I'm logged out of my computer. So I'll try to log in again. Sorry
Okay.
for the interruption. Okay. So another major breakthrough in the field of spin in this case, instead of the metallic spacer, we have an insulating spacer and two ferromagnetic layers, and we send current through the insulating layer as shown in this picture. As a result, we are talking about tunneling and the magnetoresistance associated with tunneling. So this phenomenon is called tunneling magnetoresistance. So in this case, by the other hand, if they have anti-parallel magnetization, then the tunneling probability for the electrons will be less. As a result, we will have a high resistance state. So this tunneling magnetoresistance also played a very important sorry, I have some connection problem. So this tunneling magnetoresistance also had a very important role in magnetic hard disk drives. We could move from a few hundreds of gigabytes of storage to a few terabytes of storage because of the invention of tunneling magnetoresistance phenomenon. So these two are major useful innovations of spintronics. And before I move on to the next yeah, so before I want to talk about the memory, I also want to discuss another phenomenon here, which is spin transfer torque, which is discovered by Professor Luc Bourget and Professor John Slonzewski. Basically, in this case, what we do is, suppose we have a magnetic tunnel junction or GMR device, and if we send current through the device, because when we talk about sensing information for hard disk drive, we are basically sending current through the device for reading the information. So this current will switch the magnetization of the free layer. So in hard disk sensing application, we don't want the free layer to be switched by the sensing current. We want the free layer to respond only to the magnetic field that comes from the hard disk drive. Okay, so initially people thought this is a phenomenon that's going to be detrimental, especially for magnetic sensors for the hard disk drive. This phenomenon was actually negative phenomenon, but people made use of this phenomenon to be useful for switching the magnetization states in magnetic random access memory. So people used this detrimental effect in the magnetic hard disk sensors as a useful phenomenon for spin transfer torque magnetic random access memory. So in the case of STT-MRAM, people can send current through the magnetic tunnel junction and switch the magnetization to achieve either parallel or anti-parallel states. In that sense, we can write 0 and 1. So this is the main principle of STT magnetic random access memory, and this can only store 0 and 1. Whereas when we talk about neuromorphic computing, the memory requirements are different. Okay, so I introduced the concept of neurons and the synapses. So when we discuss the electrical analogs of neurons or synapse, they should have certain phenomena. For example, in the case of biology, the neurons respond to other neurons. They receive signal from other neurons, then they produce an output signal, which is like a digital pulse. So similar thing we have to build using the electrical devices. So that's one aspect of electronic neuron. So there are some work on neurons based on spin torque oscillators by a group of Grolier and so on. So there's not too many work in this field. This is just a new field. So similarly, in the case of synapse, what we require is we need to represent the weightage associated with storing information. So in the case of electrical analogs of synapse, we can use high resistance state and low resistance states to represent the weights. In fact, in the brain memory, the weight is not just high or low, there are many intermediate levels of weights. So we need multiple resistance states. So if you look at the STT MRAM that we discussed, we have only 0 and 1 states. Whereas if you talk about the synapse for neuromorphic computing, we'll be looking at some device where we can achieve multiple resistance states. So there have been a few publications on synapses based on spintronics. So Tohoku University, they have come up with cobalt nickel multilayers based devices where they show by anomalous Hall effect that they can achieve multiple resistance state. And our group, we have worked on cobalt palladium multilayers, and we have shown multiple resistive states using anisotropic Magneto resistance and so on. So this field is, as I said, is very new, and people are just getting into this field. So there will be more works in the near future, but as of now, there are not many works related to synapse or neurons. In 2013, my collaborators, Professor Spia and me, I proposed a domain wall device, which is basically a magnetic tunnel junction in a stripe form. So normally the MTJ is a cylindrical device, whereas the domain wall device that we proposed is a stripe kind of MTJ. So in this case, depending on your domain wall position, whether it's fully parallel or fully anti-parallel, you can have high resistance, low resistance, and also the intermediate resistances. So this is something that we proposed in 2013. At that time, we were not aware of neuromorphic computing, so we proposed this for multi-level we can use this computing, particularly for synapse and neurons. So when we talk about synapse, for example, we can say that if the two layers are parallel, the resistance will be lowest, say for example 1000 ohms. Whereas if the two layers are anti-parallel, the resistance will be the highest. Let's say example, this is 3000 ohms. Then depending on where the domain wall is positioned, you may have some intermediate values of resistance. So we can use this kind of domain wall devices for synapse application. So that's the main thing that I'll be talking about the next few minutes. Somewhere in 2017, a group from Purdue University led by Professor Kaushik Roy, they came up with a neuromorphic computing circuit based on domain wall devices. So this is a simulation work. There's no experiments involved. So they have proposed that you can build a neuromorphic computing circuit as shown in this picture by using neurons and synapse. So here all these are neurons, and what is shown here, they are all synapses, and they can be built using the domain wall devices as shown in these two images. So you can have neuron by using domain wall device. So similarly, you can also build synapse using domain wall device. But this is again, as I said, this is a simulation work, and a lot of experiments necessary to realize this kind of neuromorphic wall devices. So next, I'll discuss the two main topics of the research that we have carried out. The first research topic is domain wall pinning. This is very important aspect of neuromorphic computing. So when we talk about systems that involve domain and domain wall motion, then we should be worried about domain wall motion. So if My connection is on and off, so pardon me for the audio. So in this case, the domain wall episode. Can you hear me?
Yeah, we can hear you, but I think if you can,
Sometimes it is getting break, sir. Sir, you may turn off your video, sir.
then we can get yeah.
Well, the network is going bad.
No. So if you can turn off your video, maybe then it voice will be more clear.
Turn off my video. Yes, okay, that's possible. Yeah, I'll do that.
Yeah, now it's
So now I turned off the video.
much better.
So now you can hear.
Yeah, we can hear. And
Okay, I come. Okay. So basically, any device where we deal with the domain wall motion, we cannot precisely control the domain wall motion. So this hard disk industry gave up this concept of domain wall motion as early as 1990s, because in hard disk we are storing information at a space of about 15 nanometer. So you cannot control the domain wall positions with that kind of precision. So this is one of the major problems of domain wall motion. So if you want to precisely control the domain walls, you have to some way control the pinning of the domain walls. This is very important aspect of domain wall devices. There is also another reason why we have to do the pinning, especially for neuromorphic computing, which I show using these images. So in this case, we have fabricated a domain wall device based on cobalt palladium multilayer. Here we are testing the device using curve microscopy. So you can say that white represents magnetization facing up, gray represents magnetization facing down. So what happens is we saturate the magnetic this device with a very high positive field. Then we move towards the negative direction. So we apply a negative field as high as minus 1854 worsted. So the magnetization is still up, it hasn't reversed, but you increase the magnetic field by a very small amount. Say in this case, we are increasing only by 4 worsted. Then the whole device switches from white to black, which means there are no domain walls, stable domain walls. So you just completely switch from up to down without any domain walls in this device, which means this is not useful for neuromorphic computing. In the case of neuromorphic computing, we want the domains to be positions at different places of this kind of domain wall device to store multi-level resistance, and that's not possible without any pinning mechanism. So in this case, we have prepared the film and the device as it is without introducing any artificial pinning. And as a result, we have only 2 states. We have no multiple resistance state. So this is a important aspect of neuromorphic computing, which many groups do not tackle. And this has been one of our focus for the last 4 years. We have done a lot of work on domain wall pinning. So here I show some cartoon images to show what happens when we move domain wall and how we can pin. So here, let's say I represent, I use this ball to represent the domain wall. So when we normally make a thin film, there may be some inhomogeneity in the composition, or there may be some thickness, non-uniformity, and so on. So as a result, we may have regions where there are energy barriers or energy wells. Okay, so when the domain walls move, they will find a random energy minima, and they will get stuck here. And this is the pinning region. And if you have to move the domain wall from this position to the rest of the region, we need to apply additional energy. So this behaves as a pinning site in the case of a film with a random pinning sites. So these random pinning sites may be sparsely located or they may be densely located depending on how you make your film. Whereas in the case of devices, we don't want this kind of random phenomenon. We want to control the positions precisely. So if you have to do that, you have to create energy barriers, either energy barriers or energy wells, which will act as the pinning sites for the domain walls. So this is what we need to do. And we can create these energy barriers and energy wells using two approaches. One is magnetic modification. We can do some magnetic modification. We can increase KU or decrease KU in certain regions and achieve domain wall pinning. That's what we call magnetic approach. And another approach is a geometric approach, where you have certain patterns in your domain wall device and you can use the geometrical features to pin the domain walls. So I have talked about magnetic approaches in many other places. So today I'll focus more on the geometrical approach. So geometrical approach is not very new. People have done this as early as 2008. A group of Professor Stuart Parkin, they have been using notches to pin the domain walls. So basically notch is like taking off some portion of the domain wall device at the side. So you may have notch shown in this case, or you may produce bulges like this, which is called anti-notch. So when you fabricate this kind of patterns, because of the geometric feature, you will have again energy barriers and energy wells, and you will form pinning sites. But the main problem associated with this notch is that if you have a feature size of f to create the notch, then your domain wall width will be like 3f. As a result, you will have density issues. So you cannot pack more domain walls in a given area. So that's one of the main problem of the notch-based pinning. Whereas my collaborator and we have come up with some novel approaches of pinning domain walls. So this is one design that we call staggered domain wall. So in this case, instead of making a device which is long like this, we break this into segments, and the segments are offset from one another as shown in this picture. Okay, so this is one segment, this is another segment, and they can be offset by a distance d. Okay. So this distance d will determine the pinning strength. So if the offset is too large and if the constriction is very narrow, then the pinning is very strong. So the rule of thumb associated with this staggered domain wall device is that if the nano constriction is narrower, the pinning is stronger. So we have demonstrated that these techniques work by doing experiments on pomalloy films. So we have made domain wall devices with different values of D. So larger D means very strong pinning, and smaller D means less light pinning. So you can see that when we apply 9 millitesla, we can move the domain wall from here to here, and it gets stuck at this point. And to deepen the domain wall from here to another point, we need to apply a larger field of about 16 millitesla. So at this field, the domain wall gets deepened from here, but it gets stuck here, and so on. So by increasing the magnetic field, we can deepen the domain wall from different corners. So this is one way of pinning the domain wall device, which we can use for neuromorphic computing. And we have also demonstrated that this approach works in materials with perpendicular anisotropy. So the pomalloy layers that I showed have in-plane magnetization, whereas this cobalt nickel multilayers have a perpendicular magnetic anisotropy. And even in these films, we could successfully pin the domain wall. So you can see that in this case, the domain wall is pinned at this position, and here the domain wall is pinned here, and so on. So we can move the domain walls even by spin transfer torque. So in this case, we have used spin transfer torque to move the domain wall. So pinning is possible, and we can also move the domain wall by current. So all these have been done in the studies on domain wall pinning. So now I move on to my next topic, which is reducing the energy consumption associated with the domain wall motion, which is a crucial aspect for neuromorphic computing. So for neuromorphic computing, we have to position the domain walls at different position. That represents the memory aspect of synapse. So the weight associated with synapse is determined by the precise position of the domain wall. So we have, for that we have to move the domain walls, and we can move the domain walls by many different ways. One is by the method that I just described. We can use an external magnet to move the domain walls, but this method is not practical because you cannot sell a product where you ask the customer to use the external magnetic field to move the domain wall. We don't do that. You can also implement circuits to produce magnetic field inside the chip itself, but it is very power consuming. So this is not a power efficient process. So usually people don't talk about domain wall motion by magnetic field for commercial applications. The domain wall motion by electrical current is preferred. And I have just shown some results where we have moved the domain walls by spin transfer torque. So in this case, the energy associated with moving domain wall is nanojoules per bit. Okay, this is still a bit higher. If we can reduce the energy for domain wall motion further, then it's better. So in that sense, spin Hall effect is the preferred mechanism, because people have already reported that with spin Hall effect, you can move the domain walls with energy efficiency of picojoules per bit. So here we say bit means the energy required to move the domain wall by a certain distance. So whenever I'm going to show my results in the next few slides, I'm going to talk about the energy required to move the domain wall by 20 nanometer. So my bit size I define as 20 nanometer. So the energy required to move the domain wall by 20 nanometer is what I call as 1 bit. So in the case of spin Hall effect, people have reported picojoules per bit. So many of you are already familiar with the spin Hall effect. So in the case of spin Hall effect, we have a spin Hall material, which can be a heavy metal or half a metallic system and so on. So in this case, you send a charge current through the heavy metal, and the charge current gets spin polarized. So one kind of spin goes to the ferromagnetic layer, and it can either reverse the magnetization or it can move the domain walls. So in the case of domain wall devices, we are using the spin Hall effect to move the domain walls. And the typically used material for spin Hall effect, the most popular material as of now is the tungsten. So in the conventional structure, what people do is they deposit high pressure tungsten. When I say high pressure tungsten, basically it's a tungsten deposited at a higher gas pressure in the sputtering chamber. So that's what I mean by high pressure tungsten. So they deposit a high pressure tungsten, then they deposit a cobalt iron boron on top of it, then they may have MgO and the other layers on top. So this is the typical structure for studying the spin Hall effect of tungsten, and high pressure tungsten gives the best spin Hall angle as of now. So in our design, we have modified this by a very simple approach of introducing a low pressure tungsten on top of the high pressure tungsten. This is because tungsten is a high melting point element, and if you deposit tungsten at high pressure, usually it's very granular. As a result, you will form a very rough surface. So rough surface will produce maybe a larger pinning in the magnetic layer, and it will lead to lower TMR because of the interface roughness and so on. As a result, we foresee some problem associated with high pressure tungsten. So we wanted to overcome those problems by depositing a low pressure tungsten on top of them. So we expected the low pressure tungsten on top of high pressure tungsten to retain the same spin Hall angle, but to reduce the pinning field and the roughness of the layers and so on. So we expected some benefit in the dual design. As a result, we studied this kind of structure where we have a high pressure tungsten, low pressure tungsten, followed by cobalt and boron and so on. So this is our structure, and this is the single layer structure studied by many others. So I'll be discussing the results of this reference sample and our samples, and show you how the new design works better. So these are some simple magnetic investigations like coercivity measurement, hysteresis loops, and so on. Basically, the symbol S represents a single tungsten layer. D represents a dual tungsten. So in the case of single layer film, the S2, which is the film sputtered with high pressure tungsten, showed a larger coercivity. The single tungsten with low pressure tungsten showed a very low coercivity, and the dual tungsten showed coercivity in the in-between range. So it is showing somewhere in the in-between region. Anyway, this is not a very significant result. I'm just showing for the sake of completeness. What's more interesting is the domain wall motion measurements and things like that. So here, if you look at the domain wall motion, in all the samples, domains nucleate at some point, and with the application of magnetic field, they move, they spread all over the whole measurement area. So if you look at the high pressure tungsten, the nucleation happens around minus 3.3 millitesla, and the domains start expanding as we increase the magnitude of the magnetic field, and at around minus 4.11 millitesla, the reversal is complete. So it has taken about 0.8 millitesla to complete the domain wall reversal. Whereas if you take the low pressure tungsten, so here LP represents low pressure tungsten, high pressure tungsten. 6, the number represents the thickness of the layer, tungsten layer. So the low pressure 6 nanometer tungsten, also the reversal happens, but the reversal happens over very narrow range. So from minus 1.45 millitesla to minus 1.63 millitesla, within a span of 0.18 millitesla, the reversal has happened. So this is like one fifth of what we see in the case of HP6. So the reversal happens over very narrow range in the case of LP6. Whereas if you compare the spin Hall angle, which represents the efficiency of domain wall motion or efficiency of magnetization switching, the LP6 is not good. And LP6 has very low spin Hall angle. So this is not a good material in terms of spin Hall effect. HP6 is good in terms of a spin Hall effect, but the problem is domain wall motion takes very large field range to move the domain walls. Whereas if you look at the HP3, LP3, this has similar spin Hall angle as the HP6, which means the spin orbital efficiency is comparable. Whereas if you look at the magnetic field required to complete the domain wall motion is as narrow as the LP6 sample. So this dual layer design, which combines the high pressure and low pressure tungsten, gets both the benefits of the high pressure tungsten and the low pressure tungsten. So it has very narrow domain wall pinning field, a very low domain wall pinning field, and a very reasonably high spin Hall angle. So these are the desired properties of the dual layer tungsten that we have achieved. And we have also measured the roughness and the resistivity to show that the dual layers tungsten samples are not too rough, and they are in the beta tungsten phase, which means their spin Hall angle is expected to be good, and so on. So we have confirmed all these properties in the thin film level. So now I move on to the results of the device level testing. So to test the current induced domain wall motion, we have fabricated devices using optical lithography. So the devices have electrode, a nucleation pad, and another side also we have nucleation pad and electrode. And we send the current through the device, which is basically spin Hall effect. And we we observe the domain wall motion using curve microscopy. So here we show the result of a sample with high pressure tungsten at 6 nanometer. So this is the reference sample, which means the sample studied by most other groups. So in this case, we first send a current at a density of 1 times 10 to the power 11 ampere per square meter. So that is the current sent through the device. And we apply certain external magnetic field in the Z direction. So this is a magnetic field in the perpendicular direction, 2.6 millitesla. So we apply this field and send this current and try the same field for 10 times, and the domain walls do not move. But if we keep increasing the Z field to about 4.7 millitesla, and after applying 18 pulses, then we complete the domain wall motion. So the key point is that we need a very large current density and a very large magnetic field to move the domain walls. So this field is almost very close to the coercivity of the sample. Okay, so this is not very desirable result. Whereas if you look at the case of the dual tungsten sample, so in this case we have applied 10 to the power 11 ampere per square meter, and we see that the domain wall moves. Here we applied much lower Z field, which is about -1 millitesla, and with just one pulse we could move the domain wall from this position to this position. You can see that the motion has happened from here to here. Okay, so this is the large current pulse. So we thought, what if we go to much lower current densities, whether we can move the domain walls. So we reduced the current density to further lower values of 10 power 9 ampere per square meter. So here again we can move the domain wall. So initially we see that the domain wall is somewhere here, and with one pulse it has moved half of this distance, and with another 5 pulse the domain wall has completely moved to this position. Okay, so this kind of motion has been possible at 10 power 9 ampere per square meter, and we further reduced the current density to 10 to the power 7, 6 and so on. Until about 10 to the power 6 ampere per square meter, we still see the motion of domain walls. Okay, and the field that we apply in the perpendicular direction is very little. It's only 1 millitesla, which is about 10 oersted. And this kind of field we can easily achieve from the reference layers of a magnetic tunnel junction. So if you are building a magnetic tunnel junction based domain wall device, you can get easily 10 oersted field from the reference layer of your MTJ. So this is not a big problem. With very small magnetic field, with very low current density, we can move the domain walls. So this is the key aspect of our new design. So here I show that we have carried out a very systematic study of how the field and the current density varies and so on. So here, for example, the device D2, which is the HP3 LP3 sample, the device with 2 tungsten layer, we can achieve a reasonable domain wall velocity of 1 meter per second, even for 10 to the power 6 ampere per square meter. So the velocity of 1 meter per second may be too small for memory application, whereas if you are talking about synaptic devices for neuromorphic computing, the velocity is not very important. What we need is a domain wall motion, which can be achieved by very low current density, because we are looking at power efficient devices. So the movement at very low current density is more important than the speed. Speed is not that critical for neuromorphic computing application. So we have achieved devices with a dual tungsten layer that can move domain wall at 1 10 to the power 6 ampere per square meter. So this is like 10 to the power 4 times less than what people have proposed so far. So people have achieved 10 to the power 10, 10 to the power 11 using tantalum or tantalum dope, tungsten dope is something, things like that. But our result is like 10 to the power 4 times less than what others have reported. So we tried to understand where this kind of high power efficiency comes from. So we looked at the spin Hall angle. As I mentioned, the spin Hall angle of the dual tungsten and the high pressure tungsten, they are not very different. They are more or less the same. So achieving low current density was not because of the spin Hall angle. Then we looked at other possible reason. What if the pinning field in the samples is low? If that is the reason for the high energy efficiency that we have achieved. So to measure the pinning field, we followed the protocol as I show here. So basically we nucleate a domain and measure its position. Then we apply a certain Z field and for certain duration. Then we find out how much, what is the displacement. And based on this, we calculate the velocity of domain wall motion. And we plot the domain wall velocity as a function of the applied external magnetic field Hg, and we get curves like this. So we can fit this data to a straight line, and the data in this part to a straight line, and the intercept should give you the deepening field. So if we compare the deepening field of the 3 samples, the high pressure tungsten sample shows a deepening field of 4.6 millitesla. And this is what most of the researchers report in their samples also, because their samples also have high pressure tungsten. They report around 4 to 5 millitesla, and we got similar results. And the low pressure tungsten has a very low deepening field. But as I mentioned before, they do not have a high spin Hall angle, and we didn't see any domain wall motion in these films with the spin Hall effect. Whereas the dual tungsten layer shows a much lower pinning field, like 2 millitesla, which is very close to the low pressure tungsten layer. Okay, so we believe that this low deepening field of the samples, which is formed as a result of the dual tungsten layer, is the reason for the high energy efficiency that we have achieved. So this is like driving a car in a bumped road and a smooth road. So the HP3 LP3 is kind of providing a smooth road. As a result, you can drive your car with much low energy, with very high energy efficiency. And we have also made devices to show the synaptic functions. So for this, we have also come up with a new concept called Meander Wire, which is slightly different from the staggered nanowire which I talked before. So in this case, you have segments, and you have the segments offset in a systematic way. So this design doesn't take much space. So you just offset the neighboring segments this way. So they meander. So we call it a meander wire. So this wire doesn't take too much space, and it can also pin domain walls. So we have carried out. So here again, the D determines the pinning. So if the D is larger, you will have more pinning, stronger pinning. If the D is less, you will have weaker pinning. So we have measured the pinning strength of the devices by sending current through the devices. We can observe the domain wall motion. We can take the position and plot. And if we plot something like that, it will look as shown here. So when the D is around 50%, we can see that the pinning is quite strong. So P1 is the place where we have a pinning site. You can see that the domain wall stuck there. Then we need more energy to deepen from that position. Then again, it gets stuck at position P2 and so on. So when D is 50%, we have achieved a very perfect pinning of the domain walls. Whereas if D is very small, the pinning is not very efficient. Okay, so that brings us to the summary of the talk. So I introduced the basic concepts of neuromorphic computing. I have shown that we are making use of domain wall devices to function as synapse. Then I have also shown that we can achieve domain wall pinning using geometrical methods. Then I also showed a new scheme where we have achieved energy reduction to the scale of attojoules per bit. So this is it's a very, I mean, it's a major breakthrough in our belief. So this paper is under review in Nature Electronics. So we have achieved current density, domain wall motion at current densities as low as 10 to the power 6 ampere per square meter, and energy consumption of attojoule per bit. Okay, so with that, I end my presentation. Thank you very much.
Yeah, thank you so much, Prem, for this lecture. Very nice.
Yeah, thank you.
So I could only join last few minutes. There's an echo coming.
Sorry.
One of your speaker is still active. Okay, so if there are any questions, let me start with Apu Kumar Jana. Apu, would you like to unmute and tell, or I should read your question? Well, I will read his question using microphone. What is the scale bar in domain wall motion images?
Okay, let me. Okay, I switched off one of the mics, so now I think audio is better. So the scale bar is yeah. So we have made a 10 micrometer by 10 micrometer by 40 or something like that. I don't remember the exact number, but I have given the archive. Pardon?
Maybe you can go to.
Yeah, I can show the image again. Yeah, yes, sure. Yeah, it's like 10 by 40, I think. 10 micrometer width and 40 micrometer length, something like that.
Okay. Yeah, thank you. Okay, Chandrasekhar, would you like to unmute?
So, Chandra, what's the question?
Thank you, sir. Can you hear me?
Yeah, thank you. Yes.
Yeah, thanks for the nice talk, sir. It's really interesting to see. Yeah, I have two things to ask. One thing, you said that, okay, you are moving for 20, by 20 nanometer, right? But if you take the in-plane domain wall itself can be more than kind of 200 nanometers. So how do you know that you are moving only 20 nanometers?
Okay. Okay. Let me explain. We are using out of plane devices, okay. And we are seeing okay, our devices, as you see, are like 10 micrometer by 40 micrometer. So we are still talking about micrometer. Okay. So what I'm saying is we are calculating the energy for 20 nanometer. So if 1.8 micrometer movement takes certain energy, right? So okay, then we calculate how much energy would it take for 20 nanometer. Yeah, estimating for 20 nanometer.
Oh, okay, sir. Okay.
Based on the energy it took for one point. So we are doing the same for all the calculation. I mean, if somebody has reported certain domain wall motion, so we calculate their energy also for 20 nanometer, and our estimate also is for 20 nanometer. So the reference is the same.
Okay. Yeah. Okay.
Because for future devices, we are talking about something 20 nanometer kind of bit.
Okay. Thank you. And I have the other question. Professor Shubhankar, can I ask?
Yeah, please.
Okay, so yeah, so it's very interesting to see that at 10 to the power 6 ampere per meter square you are able to drive the domain wall, right? Which is, but I mean, what is the pulse width that you are using it? What is the pulse length?
Pulse. Okay, let me see. My student knows all this better.
No, because why I
it's,
feel that it could be that okay, you are using very long pulse so that you are still be able to accumulate enough spins at the interface to switch it, to drive it. So if we
Yeah.
count
Okay.
I mean, yeah, please.
Okay, it will be like a millisecond, microsecond kind of thing. But the point is when you calculate the energy, the pulse width also is coming into the picture.
Okay.
So,
okay. Yeah, that's what I want to ask. That if the pulse width also
because
considered, then
we are not reporting. Yeah. So when we say energy, right, the pulse width is already in the picture.
Okay, great.
So if pulse width is larger, then because power multiplied by time, right?
Yes.
So the time is already inside. Yeah,
Okay.
in the energy calculation, the time is already inside.
Oh, great. Thank you. It's really interesting. If time permits, I will ask later. Somebody else is there. Yeah.
Chandra, actually, there are not too many questions. I will go to the next question, but I will come back to you. Okay?
Sure, Shubhankarji.
Yes. So, Gaurav Sharma has a question. You said changing magnetic field for domain motion is not practical solution, but you have shown domain one motion with different magnetic fields only. Or is it done by changing electric current?
Okay, so I have shown many different results. So in one case, we have moved the domain wall only using external magnetic field. So I said this is useful only for laboratory research. It's not useful for commercial application. So that is the study that we have done with the pomalloy material. Then in the other two cases, the spin transfer torque as well as the spin orbit torque, we have used external magnetic field. But that field is very low, around 10 oersted. And I say that to produce this 10 oersted, you don't need any special equipment. You don't need a external magnetic field when you make the device, because you can produce this kind of field from the stray field of the reference layer. So when you have a magnetic tunnel junction, you have the free layer where the domain wall moves, and you have a reference layer which is helpful for reading the information of the MTJ. So that reference layer itself can easily produce a stray field of 10 oersted. So that field is not very high, and we don't need some special techniques to achieve that. So it is a practical solution.
Okay. I do not see more questions. So Chandra, if you have more questions, please ask.
Yeah, Professor Prem, I would like to know that when you want to move the domain wall, first of all, we need to overcome there is an intrinsic potential to turn the domain wall angle from, I think, from null to block or something like that. So how much is that in your case, in this case?
Okay, when we say the pinning potential, basically that's talking about the intrinsic pinning
okay,
potential.
so that is
so
the intrinsic pinning.
I showed that. Yeah, I showed you the HD pinning in one of this slide. Let me show this one. Can you see this slide?
Yeah.
So here we are talking about the intrinsic pinning field.
So that is around 70
4.6 meters long.
No, okay, 4.6. Okay, 46
so 46 oersted for the normal tungsten which other people study, but in our case it's only 20 oersted.
Okay. So even the pinning potential has reduced.
Yeah, it's very low.
Oh, okay.
If you look at the samples of...
Yeah, please go ahead.
Yeah, so if you look at the samples which are used for the MRAM, typically the pinning field is like 100 oersted, something like that. So compared to those materials, this is like 5 times less.
Yeah, it looks great. Yeah, thank you. I just want to ask a comment from you that, that this is the last thing. I will stop. Yeah, so that when you see that whenever we fabricate, right, there is always a chance that you will get some artifacts at the edges, right? So what is the effect of these artifacts on the pinning of the domain walls in this kind of memory devices?
Okay, so so you are talking about the edge roughness
Yes,
and the
yes,
thinning
edge roughness, and
associated
then
with
there
the
can
edge
be some
roughness, right?
artifacts that
Uh,
that come in lithography itself
yeah,
unintentionally.
yeah. So we have not gone. You see, our devices are like 10 micrometer long.
Okay.
So that 10 micrometer width is already too high to talk about the edge roughness. When you go to maybe 100 nanometer or below, you will see all those effects. But currently, like, we are far away from those effects coming into the picture.
Yeah, I can. Yeah, they are not that prominent right now. Okay. Thank you, Professor.
Yeah, we
Thank
have
you,
not
Shubhankar.
reached that stage.
Okay.
Sure.
Thank you, Shubhankar.
Yeah, thank you. Sriram has a question. What kind of phase you got in tungsten deposition, like you said, as LPW or HPW?
What kind of?
I mean, if you see the chart window, what kind of phase you got in tungsten deposition, like you have said, LP-W and HP-W?
Okay. So the low pressure tungsten is not in beta phase, whereas the high pressure tungsten and the dual tungsten are in beta phase. We haven't, we tried to do XRD to identify the beta phases, but we couldn't see the beta phase clearly in XRD. Maybe we need to repeat with the very high skills. But we can also indirectly convey the phase information from the resistivity of the sample measurement. So if you look at some papers from IMEC, they say that you can measure the resistivity of the whole stack, and if they are above a certain number, 120, which I showed in some of the slides before. Yeah, so if they have resistivity of the order of 120 micro ohm centimeter and above, they are in beta phase. So we have used this indirect evidence to find out the phase. And the spin Hall angle measurements also confirm that we have beta phase in the double tungsten layers.
Okay, so is there a question from anybody else? Please unmute your microphone and ask. Okay, seems like there are no more questions. Or as usual, as I said, Prem gives wonderful lectures and everything. I guess is clear. So thank you so much, Prem, for giving this lecture on behalf of my committee.
Thank you.
And myself. We
thank you.
for you.
Yeah, thank you very much.
To join. And yeah, thank you so much for joining this webinar.
Thank you very much.
And see you next week. I think Professor Karthik Raman from TIFR Hyderabad will give a lecture on organic spin products. So we'll meet next week, same time. Thank you. Take care. Stay safe. Bye-bye.
Okay.